Okay, right? So these three properties are there. Now you have to say how it interacts with addition. So you have the distributive property. This you can prove x into y plus x into z. Some work to prove it. It's nice to see how these things are proved. But you will learn plenty of mathematics by doing it. Okay. So the distributive property is there. Now this is also there. So you have x less than y. You take z, then you see that z into x is less than z into y. Okay? Right? And then all these properties you can list out. So I am not going into details of that. Then you have less than or equal to, that also has a similar properties. That is not important. I mean, those properties you can list out. There's no problem. What I mean to say is that now you see your number system is very rich. So the natural numbers is now endowed with addition, an order structure, and a multiplication. Three operations are there on it. Okay, three structures are on it, and there are properties pertaining to these three properties. So that constitutes what is called a set of natural numbers. One drawback, again you can ask the same question like, given x and y, what about the solution to this equation? Does it have a solution always? Suppose x is 2, y is 6, then you know that there is a solution. Okay? But suppose x is 2 and y is 5, there does not exist any u such that x into u is equal to, or 2 into u equal to 5. There is no solution in n. Okay, so it is not always true that this equation has a solution. So that is one of the drawbacks that you have. Okay, and you can show that x into y prime, oh, that's what we have in our definition. The definition has come from this. All these properties are there. Well, let me deal with that. Now you can keep talking or proving the properties of these things. But that's not important. My point is to give you the overall structure of the real life. Now the next step is going over to what are called fractions. Now you see, fraction is what? It is actually some integer by another integer, and the integer that you have below is not equal to 0. Therefore, you can conceive every p by q can be conceived as an ordered pair p q, this belonging to n cross there is no problem n cross n because there is no 0 here. We have not introduced 0 at all. So this is it's an element of n cross. Therefore, as it is, it's an element of n cross n. Okay? So you consider n cross n. Every element of n cross n is now considered as a fraction. Okay? Now what more you have? You can have again addition, order structure, and multiplication. This extended to fractions. fraction P by Q, P1 by Q1 and P2 by P2. I don't want to write it in the order pair language. Use the conventional language that we have. This is, you know, is P1 Q2 plus P2 Q1 divided by Q1 Q2. Or in other words, the ordered pair whose first element is P1 Q2 plus P2 Q1 and the second element is Q1 Q2. Okay? So that is how you define it. Right? Okay? That's how the sum is defined there. Now one can prove these things. That is, you can prove all these properties mainly. See, here one thing is that we have not used anything new to define this. You know, it's a very sophisticated definition. Okay? It is not defined as P1 plus P2 divided by Q1 plus Q2. Because that would have been your instinctive way of doing it. Okay? But it is not. Right? So this is to facilitate a certain addition rule that is familiar to you from our day-to-day experience. So it is sophisticated. That is why addition of fractions is a problem for students, because it is not straightforward definition. It looks crazy because you are writing P1 Q2 plus P2 Q1. Why do all this acrobat? You might ask. Yes. Okay. But let us see the experience of this. Suppose you have a cake. Okay. And you have 1/3 of this plus half of this. What do you get? It's our experience. You take half of it and then 1/3 of it. What do you get? This is 1/3. What do you get? Okay. You can write this as, see, how do you write this? You divide everything more sharply, okay, into 6, because 6 is the what you call LCM of 2 and lowest common multiple of 2 and 3. Therefore, 1 by 2 will look like 3 by 6, and then what is this? This is 2 by 6, and there you write it as 5 by 6 because the denominator is the same. This is our addition. What is this? This 3? 3 is essentially, see, what you have is 6 is essentially your 2 into 3. And what is this 3? 3 is equal to 3 into 1 plus the other one is 2 into 1. That's what we have. Okay, that's how addition is taken. Because addition has to match with your experience. That's what that's what we have to see. Now there are a lot of intricacies that come with this kind of. So let us explore this one. Okay. And then you can prove all the properties of addition, multiplication and so on. But one thing that you observe is this. You have suppose x1 by x2. Then you write this as y1 by y2. Of course, obviously when x1 equal to y1, x2 equal to y2, you write it that way. But even in other cases, you write it y. Already you have 1 by 3, 2 by 6, then 3 by 9, etc. They are all the same fraction from your experience. So you have to reflect that here. So you say that they are so provided the following holds, that is x1 y2 equal to x2 you write this is, they are the same. I don't write them equal, I am writing they are equivalent provided x1 y2 equal to x2 y1, x1 y2 equal to x2 y1. That's what you have. 1 by 3 is equivalent to 2 by 6. Y 1 into 6 is equal to 3 into 2. Okay, so this is the condition for equivalence. So this is so now what you have on n cross n, you identify every element with a fraction. You have an addition. You have an equivalence relation. Equal to notion is there. Then you have what you call addition, and then you have what you call an order structure. What do you mean by order structure? Now, given x1 by x2 and okay, we define an order structure. We say this is less than y1 by y2 if x2 y1 is less than x1. This is the definition. Similarly, we say x1 by x2 is equivalent to y1 by y2 if x2 y1 or you have x1 x2 is greater than sorry x1 y2 is less than x2. Made a mistake here. So x1 y2 is greater than. Now see, we are using our addition, multiplication and less than or greater than or equal to that we have defined on n to go to n cross n and define the structure. Because this is your notation that you are using, and this is if this is true. I mean, this is quite easy to find out because given x1 y2, x1 and y2, you have x1 y2. Given x2 and y1, you have x2 y1. Now given two natural numbers, you can compare them. So whether this is less than that or this is greater than that or they are equal. Accordingly, we introduce the order structure. Okay, that's what it is. Now one of the properties that you can prove is this, that given x2 and y1 by y2, either or x1 by x2 equivalent to y1 by y2, or x1 by x2 less than y1 by one of the three properties are valid. Moreover, see, one of the important things that you can prove is this: x1 by x2 given, suppose it is less than y1 by y2, then there exists x1 by x2 is less than z1 by z2 less than y1 by. What does it mean? It means between two fractions you can always interpose a fraction, and whenever they are not equal. Okay, this is very, very, very important and deeper property of the fractions. Okay, now from fractions we manufacture the so-called rational numbers. Okay, so I just say what rational numbers are. Okay, then of course you have the multiplication defined, x1 by x2 into y1 by y2. That is pretty straightforward. This is x1 y1 by x2 y2. It is the ordered pair x1 y1 comma x2 y2. This is the definition of multiplication. So you have both addition, multiplication and order structure extended to the fractions. Okay, equality is now called equivalence because of the simple reason that things like 1 by 3 is not equal to 2 by 6. Because one is as points in n cross n, they are not the same, but they are having a relation, and that relation is what we call equivalence. Okay. Now from fractions we manufacture what are called rationals. This is what we do. Suppose you have got all the fractions which I denote by n cross n with all these structures plus, less than, and multiplication. Now you see that this is a very, very, very important thing that one does in mathematics. Take an element. Now we define a relation. Okay, we define a relation. We write x1 by y1 or x1 by x2 is related to y1 by y2 if and only if this is the definition: x1 y2 equal to x2 y1. This is the definition. So we say that x1 by x2 is related to y1 by y2 if x1 y2 is equal to x2 y1. What sort of relationship is this? So given two fractions, either they are related or they are not related. That's what we say. So given they are equivalent or not equivalent, which means either this may be less than that or the other one may be less than the other. Okay, as we have defined earlier. So what you do is choose an element, collect all the elements that are equivalent to it. Put them in a block. Okay. So given two elements in n cross n, either they are in the same block or they are in different blocks. Okay. Now you can prove that this is an equivalence What does it mean? It means x1 by x2 is related to itself. This is what you call reflexive. Then x1 by x2 is related to, this is reflexivity for every x1 and x2. Then you have x1 by x2 is related to y1 by y2 implies y1 by y2 is related to x1 by x2. This is what we call symmetry. Then you have x1 by x2 related to y1 by y2, comma, y1 by y2 is related to z1 by z2 implies x1 by x2 is related to z1 by z2. So this is what we call transitivity. It is not any type of relation, but it's an equivalence relation. That means it satisfies all the three properties, namely reflexivity, symmetry, and transitivity. Now you know that if on a set you have an equivalence relation, then you know that it partitions n into what are called equivalence classes. That means it is broken down into disjoint sets, and this can be written as a union of disjoint sets. And if you take one such subset, it will contain only elements which are equivalent to each other. If you take one element from one set and another element from another set, then they are not going to be related at all, okay, through this equivalence relation. So that's how this breakup comes. Okay, so you have collected all these sequences. For instance, example is, if 1 by 3 is here, then you have 2 by 6 is there, 3 by 9 is there, 27 by 81 is there, etc., etc. All these elements are there. They are equivalent to each other. Okay, but you won't see 1 by 2 in this, because 1 by 3 is not equivalent to 1 by 2. So that's what you have.